Good morning, ma'am.
Good morning. Well, remember that yesterday we have defined this Stirling number of first kind. Just you recall this Stirling number of second kind. We have discussed that this is capital S N K. This was the notation. Okay, and this was actually that. I mean, this is the number of partitions of an n set into k blocks. You just remember SNK is the number of partitions of an n set into k blocks. Well, we have seen also some examples, and then I had asked you to check this recurrence relation about this S and K. This is capital S, okay? It satisfies this reference relation. S and K is equal to S n minus 1 K minus 1 plus K times S n minus 1 K. It satisfies this recurrence relation. And I had asked you to think over this, why this recurrence relation is true. So, did you, get the proof? Has anyone thought about this?
Ma'am,
Have you thought? Huh? Tell me.
can I say?
Ah.
Ma'am,
Yeah, please. Please
yeah,
tell. What's your name?
yeah, Karthikeyan.
Okay. Karthikeyan. Okay.
Number of ways of dividing n things into k blocks
Uh-huh.
is same as number of ways of dividing n minus 1 things into k blocks and then adding the remaining element to any k of them
Okay.
plus
Huh.
plus
Huh.
taking the n minus 1 blocks into k minus 1 blocks and then keeping the extra elements separate.
Okay. That's separate. Okay. It is, it is like that. What you are saying is, let me write. Ah. See, let us take, where is the cursor? Well, I can take that. Let X be an n set. Huh? So, we'll take that X contains n number of elements. Let X be an n set. Well, and X be an element here. X belongs to X, suppose. Huh? Yeah, the same argument actually what Karthikeyan said, that I am writing in proper way. So we are taking any element small x in this set, in this n set. So the S and K is the number of partition of x into k parts. Okay, we are taking this S and K is the number of partition of x into k blocks. Well, number of partition of X into K blocks, that you can divide into two parts. Okay, so here we'll take that, set of all, partition of X into K blocks in which X, okay, I'll write this one. This is, we can write this. This is cardinality of, this is cardinality of the, cardinality of, or a number of, I could have written this number of also, okay, no problem. This number of partitions of X into K blocks such that this singleton set X is a block. Okay, singleton set X is a block here, and the other kind of partitions in which singleton set X is not a block, plus number of partitions of X into K blocks such that this singleton set X is not a block. This is not a block. Well, so this, first part, let us take this, the cardinality of C1 and cardinality of C2. C1 is a collection of all the partitions of X into K blocks so that X, singleton set X is a block. That is C1, the collection. And this cardinality of C1, see, if we remove the singleton set X, okay, if we remove this singleton set X, then we will get a, just I want to tell that there will be a one-to-one correspondence between this number of partition of n minus 1 set into K minus 1 parts and this collection C1. So whether you get that cardinality of C1 is equal to the number, number of partition of an n minus 1 set into K minus 1 block. We'll get this because we can get a one-to-one correspondence, because that we can get because there exists an one-to-one correspondence between that C1 and that partitions of n minus 1 set into K minus 1 block, and partitions of n minus 1 set into K minus 1 blocks. Whether you get this one-to-one correspondence, it is clear to you. Students, do you understand this correspondence?
Can you explain one?
Yeah, sure. That is why I am asking whether you have understood or not. Okay, let me go to the next page. Okay. So, that one-to-one correspondence, how do you get this one-to-one correspondence? You take an element of this C1, okay, this collection. So, what is an element of C1? C1 is consist of a partition of an n set in which X is a block, okay. So an element say, let us take this. Let P belongs to this C1. Okay, P is an element of C1. So what is P? So this P is basically it is consist of let me take this S1, S2 and suppose Sk minus 1 and Sk is this singleton set. Okay, and this each of these SI they are subset of non-empty subsets. Okay, remember that in case of partition we take these subsets with non-empty subsets. So they are subsets of this X, non-empty subsets of X. Okay, so this P is a partition of X. This is a partition of X into K blocks, and this singleton set X is a block. Singleton set X is a block. So P looks like this. It is clear to you? Okay. So this is an element from C1. C1 is consist of this kind of partition. Then from here, I mean we are saying the one-to-one correspondence. So this element P that will map to, I mean that maps to the collection. I mean I'll drop this singleton set X and I'll map, I mean this, I'll map to this collection, or this is a partition. Okay, so this is a partition of this K, I mean n minus 1 set, that is X minus X. So this is a partition, say this is P prime. Okay, let us say this be P prime. And this is a partition of X minus singleton set X, which is a, I mean n minus 1 set. Understand, the cardinality of X is n, therefore this capital X minus this element small x, this is an n minus 1 set, and they converge sexually. This is one-to-one correspondence. So both way that conversely, if you take any, I mean any this partition, this P prime of X minus X into K minus 1 blocks. Okay, so this, if you take P prime be any partition of X minus X into K minus 1 blocks, then I mean we can get this P prime union this singleton set actually. Okay, this union this singleton set is this is a partition of X into K blocks. So did you get this one-to-one correspondence? Now it is clear to you?
Yes, I am.
Yes, ma'am.
Okay, fine. So because of this one-to-one correspondence, we get that cardinality of C1 is actually equal to number of, I mean this partition of an n minus 1 set into K minus 1 blocks, and that is why we get this inequality. It is clear? Okay. So this is how we get this equality. This equality will get. Cardinality of C1 will be equal to S n minus 1 K minus 1. That is the number of partition of an n minus 1 set into K minus 1 blocks. Fine. Okay, so one part we have done, I mean the cardinality of C1 that we have got. So next we shall find out the cardinality of C2. Cardinality of C2 will be what? Cardinality of C2. What is C2? By the way, C2 is actually C2 is a partition of an n set. I mean X we are taking partition of X into K blocks, and in which the singleton set X is not a block. Okay. So I mean I want to say that if P belongs to C2, P belongs to C2, P belongs to C2. Well, if P belongs to this collection C2, then P will be looking like this. This partition P is of the form S1, S2, Sk, well, and each Si is a non-empty subset of X, and none of them are equal to the singleton set. Okay, and Si, none of this Si, I mean, is equal to the singleton set X, no Si. Okay, for all I that I want to keep. So, singleton set X is not appearing as a block in a partition that belongs to this collection C2. Right. So, it is consist of this type of partitions. Well, fine. So, next what I shall do is the following. I will consider, okay, say, let us take this Y is the set X minus the singleton set X. Okay. So now I will consider a partition, I mean I'll consider a partition of Y. Let P prime be a partition of Y into K block, Okay. P prime be a partition of Y into K blocks. Well, then I mean say this P prime is of this form. Okay, let me write. P prime is something like Y1, Y2, Yk, and each Yi is a non-empty subset of Y. This is non-empty subset of Y, and their union, you know the meaning of the partition. Union of Yi will be equal to Y. Okay. So, given any partition P prime of Y, I mean the element X is not there in any of these, I mean subsets Yi, right? Element X is not there, X is not there in any of these Yi, okay, for any I. So then next, I shall include this, I mean, and you know that each of these Yi is a non-empty set. Now I shall include this element X in any one of out of this K number of subsets. In any one of them, I shall include this element X. I shall include this element X. Well, that how many ways I can do? How many ways that X I can include in any one of these K subsets? How many ways I can do? Tell me. How many ways I can?
K.
K, man.
Yeah. K. Very good. There are K subsets, and I can put in any of these K subsets. The element X I can put in any of these K subsets. Well, and we know that none of these Yi is an empty set, right? And therefore, here none of these yi will be singleton set x after inclusion of element x. So then now we include x, okay, then we include x in any one of these subsets y1, y2, yk. Right. So without loss of, I mean, okay, then see, it will look like this. Suppose in y I I'll include. So that means suppose I'll include in ith set. So it looks like this: y1, y2, yi union this singleton set x and this yk. I mean, we'll get this. Okay, we'll get this collection of subsets, and none of these, I mean, subsets will be singleton set X, because see, yi was a non-empty set earlier and it has some element. Okay, it has some element of y it contains. So it is not a singleton set X. So therefore, this is a partition of X into k blocks in which singleton set X is not a block. So therefore, I mean, this belongs to C2, the collection C2 we have taken. Fine, this belongs to the collection C2. It is all right. Okay. So given any partition P prime, that we will get that given any partition P prime, we get k number of such partitions of X that will map to k number of, I mean, we can generate actually from any partition P prime of Y, we can generate k number of elements of C2. Okay. So this is how, I mean, that all the and the vice versa actually. Okay, and the vice versa, that we can do. I mean, this correspondence. So therefore, whether you agree that cardinality, so we get that the cardinality of K2 will be k times the number of partitions of y into k blocks. Okay, is k into that number of partitions of y. This is not x I multiplied by. Okay, this is multiplication. I am taking this in multiplication here. Multiply, not x. K into number of partitions of y into k blocks. Okay, and this is exactly this. I mean, of S of y is having n minus 1 elements into k blocks we are partitioning. So this is exactly the number k into S n minus 1 into sorry, S n minus 1 k. Hope we have understood this. It is all right. Or
Yes,
any
sir.
doubt? Yeah. Okay, if you have any doubt, you can ask also. Otherwise, let us move to the next. I mean, so
Doubt in the
ask,
final equation, ma'am, any of the elements can be that x that we are considering, right? So why aren't multiplying the entire expression by n for the original
okay.
on the
Oh,
right hand?
by k you are saying original expression by k. Huh? This
No,
multiplication you are saying the multiplying by k.
no, ma'am. In the original, Sn k equals Sn minus 1 k minus 1 plus k Sn minus 1 k. In that,
Yeah.
why multiplying the entire
This equation, huh?
Yes, ma'am.
You are saying this k, why I am multiplying this k?
No, ma'am. The entire right hand side, that entire sum, like, why aren't we multiplying it with n? Because n
Where?
is the x we are considering.
Where I am multiplying n? Please tell me which one.
Ma'am.
Where's the entire one I am multiplying?
Ma'am.
Huh?
She's telling you considered one element x, right, out of the whole set. And
Oh.
then that's how you solved it, right? She's telling you can consider that x itself n ways, right?
No.
Is that your doubt?
That is okay. You are saying that since we have taken x be in any element and this capital X is having n number of such x.
Yes, ma'am.
That is why okay. No. The thing is that here just you consider any element x actually. Just I am fixing any element. I am not working for this element x. I am fixing an element x. So once we fix any element x, so what I am doing this, where is that? Okay, this, I mean S and K, that number of partitions here, okay, this equation will come. That number of partition, this is actually this S and K is the number of partition of X into K blocks. Okay, so the collection here I think I could have included one more thing. Let us include this statement that here I am taking the collection of all partitions of X. That we can write. I mean, this is exactly the same thing actually what I have written. SNK notation I have used, and here I will write this number, exactly the same thing I could have written here, number of partitions of X. Partitions of X into K blocks. Okay, into K blocks I am taking. I am taking this, or in other words, this collection C, if you take, that is the collection of all partitions of X into K blocks. Okay, that we are writing C1 union C2. So that will be true for any arbitrary element you select actually. It is not, okay, that it is, I mean, just we are fixing an element and it is, what I will say that this union is always true actually. We are writing this union basically. Okay, you are interested on this collection of all, I mean, partitions of n set into k blocks, that we can write. For our, I mean, the proving purpose, we are just taking an x actually, considering an element x. It is, we are not proving that this, okay, for every element x kind of thing.
Okay.
Just you think it is not depending on that actually. Okay,
Thank
this is okay, proving technique. Okay, I mean, you try to convince yourself, think yourself. Okay, you may not able to get convinced immediately here in the class. Okay, think carefully, you will get it. Okay, fine. So then, this is about Stirling number of second kind. Before I go to this Stirling number of first kind, I want to tell you another important, I mean, parameter you can say, or important concept, that is partition of an integer n. Okay, partition of a number. Okay, partition of a number. Partition of a number n. N is an integer. This is an integer. I mean, in fact, with a positive integer. Positive integer. This is a positive integer. Okay, I am writing greater than.
Excuse me, ma'am.
Huh.
This is only for positive integers, or we are considering just a special case of positive integers?
No, for all positive integers. Okay, partition of any positive integer.
Ma'am, like for negative integers, can we define the partitions like this, or it is only holds true for positive integers only?
Yeah, this is for positive integer. Okay, I am considering for positive integer. And similarly, I think this can extend to negative integers also. Why not?
Okay.
Okay, negative integer means some will be negative, positive mix of years in that case. Okay, so here I am considering for positive integer, partition of a positive integer. Well, so what is the meaning of partition of a positive integer? So in this case, I mean the partition of a positive integer means the number of ways in which this n can be expressed as a sum of positive integers without counting order. I mean, let me write down what is the meaning of partition, and then I'll give example. So here, partition of a number n means this is the partition. Okay, there is a notation for this. That Pn, let me write down this Pn. This is the total number of partitions of n into positive integers I mean that 0 also we are not considering. No part will be considering that 0 as a part of this. Okay. So this is the Pn is this notation for total number of partitions of n into positive integer. So a partition of n is n is an expression, or what I will say is a sum of positive integers. I'll say is a sum of positive integers, sum of positive integers, which is equal to n actually, sum of positive integers which is equal to n, and in which the order is not considered. Okay, I'll tell you what does it mean. In which order is not considered. Order is not considered. I mean, what is the meaning of this? Order is not considered. Say, for example, we will take that. Let us take this partition of 5. Say, for example, n equal to 5. Suppose it is. Then this partition of n, I can write down what are all, say partition into say 3 parts. Let me take that partition of 5 into 3 parts. Say for example, I am taking into 3 parts. So what are all? We will get that 3 plus 1 plus 1. This is one part. So that, I mean, order we are not considering means we will count this 3 plus 1 plus 1, or that 1 plus 3 plus 1, or that 1 plus 1 plus 3. All will be considered as only one partition. Okay, this will be considered as one partition. You understand? So this will, I mean, this ordering will not be counted. This will not be counted. This all will be counted as same, only one part. So that is what I mean that the order is not considered. Well, so just you recall, when we were solving this equation that say x1 plus x2 plus x3 is equal to 5. So that total that number of solutions, so integral solutions of this equation with xi is greater than 0, positive integral solution. So number of positive integral solution of this equation, when we were looking into this number of positive integral solution of this equation, solution of this equation. So in that case, we do consider that you consider this 3, 1, 1 or this, I mean, you count them as different, right? 1, 3, 1 or this 1, 1, 3. They will be counted as 3 solutions. Okay, they are 3 solutions because these variables are involved. This is x1, this is x2, this is x3, and here x1 is 1, x2 is 3, and x3 is 1. Because we are distributing to, I'll explain further. We are distributing to these 3 variables. Okay, or we are distributing to labeled boxes. Okay, we are distributing to labeled boxes actually, labeled box. Five objects or 5 balls we are distributing to 3 labeled boxes. So I'll write down this complete actually this distribution that I mean the distribution of identical balls into that I mean distinguished or different or labeled boxes kind of thing. I'll look at all cases, I'll summarize and I'll write down. But just you understand here that when we are solving this equation into positive integral solution, we are looking into, in that case, they are all considered to be different. Okay, they are considered to be different. I mean, that answer of this different solution of this equation, right? But whenever we look at the partition of a integer, all 3 will be taken as the same partition. All 3 will be taken as the same partition. Understand? So then next we are looking 5. We are partitioning into 3 parts. So therefore, the other possibilities will have the another one is 2 plus 2 plus 1 only, right? And will not have any other. Okay, will not have any other partition in partition of 5 into 3 parts, because I have told you these are all same, that 1 plus 2 plus 2. Okay, there I mean will not be considered as different. This is same as this one, the one, right? So here the partition of 5 into 3 parts, we are getting only these 2 actually. So what are all the partitions of, I mean 5? What are all possible partitions of 5? So that is the P5, total number of partition of 5 in 5, total number of partition of 5 into positive integers. Okay, into positive integers. This is what we consider the, I mean partition of this 5. Okay, so how many are there? You tell me, what is this number? What are all the partitions? First you list here. This is a small number, so therefore we'll able to list all of them. So 5 is 1 part. The next will be, I mean partition into 1 part. Partition of 5 into 1 part only. That is 5. Into 2 parts, you get 4 plus 1. Into 3 part, I have already written here. 2 plus 2 plus 1. And then into 4 parts. This is into 3 parts, then 4 parts. 4 parts means 2 plus 1 plus 1 plus 1. And into 5 parts then. All will be equal to 1. Each part is equal to 1. So these are all the partitions of the number 5 we are having, will get. So how many of them are there? There are how many? 3, 4, 5. How many? Okay. Another one I have missed. You did not notice it, right? Another one I have missed. Partition into 2 parts. I could have written 3 plus 2. That I have missed here. These are all, I hope. Do you agree that we get these 7 are there? These are all the 7 partitions we'll get. Whether these are the all. Answer is 7 or some more. You tell me. Whether it is all right, students? Correct. Okay. This is what you will get. So this partition of this any number you can write also like this. Huh? I mean symbolic way you can write that whatever I have told you. Well, say you could have written that. I mean just symbolic way. What I am saying, a partition of n is actually it is like this. You can write also n1 plus n2. I mean, all possible k parts actually. N into k parts I'll write. Then into k parts is, it will look like this. Huh? Plus nk, and none of this ni is equal to 0. And here ni are integers. Ni are, I mean, positive integers. So you can say means it is not 0. Are positive integers, and I mean this order is immaterial. Okay, so this order, this is on order. This sum is actually this is on order. Okay, so here order will not be counted without counting order. So here this ordering will not be counted here without counting order. You can say that without counting order. Okay, this is how. See, this, I mean, 5 is a small number, that is why we could easily find the value of P5, total number of partition of 5. But in general, it is not so easy. In fact, I mean, we may have, I mean, some, okay, that I mean, in terms of recurrence relation and all those things, we can have a representation for this P, but in general, we cannot have a formula in terms of N only. So let me introduce here one more, I mean, notation that is associated with partition of number. So another notation I will have is this. For k is again an integer greater than or equal to 1, less than or equal to n, and integers kn, integers, will use this notation. Let pkn, this pkn, this denote, pkn denote the number of ways in which, let me write this, denote the number of ways in which n can be expressed as the sum of at most, at most, I mean notice this, at most k positive integers, at most. So pkn is actually the number of partition of n into k or fewer parts. Okay, so this pkn is actually number of partitions of n into k or into at most k parts. We can write that is same as into at most k parts. That is pkn. Well, so therefore, from this notation, of course, we'll have this k is equal to n. Pnn. This pnn would have been your pn, right? Pnn would have been your pn. Pnn is right. Therefore, from this notation, this is equal to pn. Well, This here using this notation, what is the value of say P25? P25. So number of partition of 5 into at most k into at most k parts, k equal to 2. So therefore this value is equal to 3. That either one part into one part or two parts. So look at, so this value will be equal to 3. So similarly here P35, P35, P35 means partition up to 3 parts, up to 3 parts. So therefore you are having this 5 up to this actually here. 5 parts you can have 5 such actually, 5 such partition of n. Well, so there is a recurrence relation for this pkn. I'll just write down, I'll not write, I mean the proof and all I am not giving. It is available if you are interested, you can read, because okay, we don't have enough time for this discussion. You go through actually that we can have for positive integers nk, positive integers nk with k less than or equal to n, this pkn. Sometimes people do use small p or big, this capital P. I'll use capital P anyway. I'm using capital P. Okay. Pkn is equal to pk minus 1, and you try to prove if you can prove yourself. I'm not giving the proof here. So that pk satisfies, pkn satisfies this recurrence relation. Okay, pkn satisfies this recurrent relation. So actually, I mean, with all these notations we have seen so far, I will discuss about, look at this distribution of, I mean, when we are looking into this solution of this equation that x1 plus x2 plus x3 is equal to 5. Okay, or in general n, x1 plus x2 plus xk is equal to xk is equal to n. So we are looking into the number of solutions of this equation in general, that x1 plus x2, earlier we have seen actually the number of solution, non-negative integral solutions of this equation. Okay, number of non-negative integral solution of this equations, you just remember, number of non-negative integral solution of this equation. What is this number? It was n plus, you just remember, k minus 1, choose k minus 1 or choose n, both are same. This is what you are getting, the number, or this is n, choose n, both will be same, right? So in this case actually what we are doing, so actually now I'll give the complete summary of the distribution of balls into boxes. So distribution of balls into boxes. So it may happen that all your balls are identical, boxes are, they are distinct, or all the boxes may be identical also, and balls may be distinct. I mean, there are two possibilities. Okay, so see, the possibilities are like this. The balls have, I mean, here I'll tell you the balls, maybe they are identical or distinct. There are two cases you can have, identical, or I mean, they are distinct balls. Distinct. Similarly, the boxes, they may be identical, Okay, identical or distinct. And another question is that box is, whether these numbers, they are positive integers. We are considering all positive or non-negative. See, if we are considering these numbers as non-negative, means some variable may be equal to 0 also. Whenever we consider this non-negative, then some variable, say x1 may be equal to 0. We are considering 0 also. So if x1 equal to 0 means, in that case we can say that the first box may be empty. We are keeping some boxes empty. Whenever we are looking into non-negative integral solution, some boxes are empty. 0 means that box is not receiving any ball, any object. So therefore it is empty. So here also these boxes have that two possibilities, that is empty or not empty. Okay, empty or non-empty. Okay, so this is also, we have these two cases, empty or non-empty. Okay, non-empty. So these two cases. So therefore in this total, distribution. Okay, so total we are having the 8 possibilities. So 8 possibilities, combining all these possibilities, the distribution of balls into boxes, this distribution problem, this distribution of balls into boxes, this problem, that we can we can divide into 8 category actually. 8 category we will have. So whether identical, distinct, or empty, non-empty. So each case you are having 2 possibilities. Okay, we'll combine all 3 possibilities. So therefore we'll have 8 kind of different ways of distribution of these balls into boxes. I'll summarize all those 8 cases, and I'll tell also the number of ways, the formula or the answer, what we will get, the number of ways of distribution. So before that, before I go to summarize this, consider these 8 cases of distribution of balls into boxes. I will just ask you one thing. Here in this equation, we are considering all non-negative integral solutions of this equation. If I consider the number of, positive integral solution of this equation, how many, what will be your answer? So here you note this one, what you will get, that number of positive integral solutions of this equation, x1 plus x2 plus xk is equal to n. That means here we are considering is xi is greater than or equal to 1, positive integral solution. So here in this case you had this xi was greater than or equal to 0, is xi is greater, may be equal to 0 also. But here it is greater than or equal to 1. So what will be this actually? What is your answer here? What is your answer here? What will be this number? See, you can modify now. You can, is xi is greater than equal to 1. So why don't you define a new variable yi, that is xi minus 1. Earlier we have done this way.
n minus 1 ck minus 1.
Yes. So here, if I replace, this new variable yi, I will consider xi minus 1. So now, if you consider this equation, that in terms of, y1, y2, up to this yk, okay. So on the other side, you are getting n minus k. Fine. You are getting n minus k. y1, y2, in place, that xi is yi plus 1, yi plus 1, fine. And therefore, I will get this equation, and here in this case, yi will be greater than or equal to 0. xi is greater than or equal to 1. So therefore yi will be non-negative. And now we are considering the number of non-negative integral solution of this equation. Number of non-negative integral solution of this equation with this, okay, yi greater than equal to 0. So therefore that answer will be here, this n minus k, I mean that n minus k plus k minus 1 choose this k minus 1. But here this k minus k plus k that gets cancelled and you are left with n minus 1 choose k minus 1. This is what you answer. Understand? So this, I mean this answer or solution of this equation, what does it give? This gives that distribution of n number of identical balls. Balls are identical and boxes are distinct, k boxes. We are distributing n identical balls to k boxes so that no box will remain empty. No box remains empty. So in the previous case, some boxes may be empty. Okay, some boxes may be empty. Non-negative integral solution means boxes are distinct, k distinct boxes are there, but in the distribution some of the boxes may or may not be empty, may be empty. But here no box can remain empty. Okay, this is the difference between these two. Well, so now I think we are ready to consider this, all these possible kind of problems of distribution of balls into boxes. So I'll write down this distribution problem into I mean that in a tabular form. Let us write. Okay, so here I mean the balls we can have so the I'll tell these balls are distinct or not distinct. Boxes are distinct or not distinct. Okay, and empty boxes will be allowed or not. Empty boxes, whether we'll have any empty box, this is allowed or not, yes or no. And here we'll have number of ways. Okay, so total we'll have 8 cases. I have told you that each one is having these are the 3 parameters you can say, and each one is having 2 possibilities, right? So first case, let us take distinct, balls are distinct, boxes are also distinct, and empty boxes or no. Okay, let us allow the boxes first empty. Some box may remain empty. Okay, some empty boxes are there. Okay, that we will allow that. Tell me, what is your number of ways of this distribution? Okay, and before that, I'll tell you this: number of balls is n, and number of boxes is k. Okay, here we consider number of balls is n, and number of boxes is k. K is the number of boxes, and n is the number of balls. Tell me, what is your answer here? What is it? How many ways you can do this? How many ways you can do this? You can answer. Huh?
K to the power n.
Yes, you all are correct. K to the power n. Yes, K to the power n. Okay, so how do you get this? Can anyone explain? Why
Every
do you
ball
get
has
this?
k choices.
All n balls have k choices.
One by one you can tell. Tell who will tell now. Who all were telling? Who all are tell? All are there?
Every ball has k choices.
Okay. What is your name?
Satvik Bansal.
Satvik. Huh?
Yes, ma'am.
Okay, Satvik.
So every ball has k boxes in which it can go. So for each ball, k choices. So k into k, that is n times. So k raised to the power n.
Yeah. See, look. Okay, you can also think this problem in this way. That will be also easy to you. Okay, this is same as the number of functions from a. Okay, you might have done this problem that suppose I am having a set x and set y. Set x is this and set y is this. And here we are having n number of. Okay, here its cardinality is equal to n and its cardinality is equal to k. So, number of functions, okay, number of functions you will have from x to y. So, this number of functions, how many functions? Number of functions you can have from x to y. So, these are your balls. So, these are your balls. And these are the boxes. I mean, all the balls are distinct here. Okay, in these functions, we do consider the elements are all distinct. And here in this set also, this, I mean, elements of y are distinct, boxes are distinct. So here that how many ways that you can get, I mean, you can find the functions. So function means what? Every element of this domain set should have a image. Okay, every element of this domain should have a image, right? And the function may not be on two. So some of the boxes may remain empty also. No element from x will may that may not map to, I mean, some element in y. Okay, this may not be onto function. So therefore, some of the boxes may be empty. That emptiness of boxes will be allowed. But all the balls should have a image. All the balls that should map to some box. Okay, all the balls should map to some box. So there are n number of balls. If I consider any arbitrary ball, so that has how many possibilities? How many that can map to any of these elements? Image of this element can be any of these. Okay, that can map to any of these boxes. So number of possibilities to map this element is k. Similarly, this also can map to any of the k boxes. Okay, and obviously no ball will be distributed to two boxes. That is why it is a function. I mean, no element will have two images. Means no element will be mapped, I mean, distributed to two different boxes. Okay, so each one is having k possibilities. Okay, so therefore there are n number of balls and you get your number of which is k to the power n. Okay, so this is exactly this number of functions you get from an n set to a k set. Okay, so this is same as this number also. You can note it. You can note it. This is the number of functions from a n set to a k set. This number. You can think in this way also. Number of functions from a n set to a k set. This is exactly this also. Okay, you can think in this way also. Okay, fine. So then, second one. Second case, I'll come that second one will be distinct balls. Okay, all these four things I'll take distinct, distinct, and here also distinct, distinct. Okay, distinct. Okay, then no. Here, no box will remain empty. No box will remain empty. Boxes are, boxes are all distinct, balls are distinct, and no box will remain empty. Oh, another thing you note down, that I was wanted to tell you that, okay, I was one, yeah, you note down one more thing, huh? Just I'll tell you. What is this Stirling number of second kind? That remark I was wanted to tell you about SNK, that is Stirling number of second kind. This was, what was this? Partition of an N set, partition of N set into K blocks. Okay. So this is, our definition was partition of N set into K blocks. And can we also think this as, this is same as the number of ways of distribution of n, n distinct balls, into k, identical boxes, so that nobody, okay, whether this is equal to that, I want to tell you that whether this is true or not, you answer that. Oh, okay, where I am. This is not. So this is whether this SNK is distribution of n number of n distinct balls into k identical boxes. So this is equal to number of ways to distribute n distinct balls into k identical boxes. Whether this is true. See, in the n set, that n set we are considering, in the n set we are writing the elements, say x1, x2 to xn kind of thing. Okay, we are writing this n set be like this. So here, say, I'll partition into two. Say for example, I'll partition into two. So in, say, suppose I am taking x1, x2 is in one part, and the remaining x3 onwards, x, here xn will be in the other part, k equal to 2. So whether this is, this, and then other way, suppose I would have taken that x2 and x3 in one part, and the remaining, that x1, x4 to xn. So these two will be treated as two different partitions, right? Say P1 is one partition and this is P2. P2 will be different partition. In P1, x1, x2 is a block or cell, and here x2, x3 is another block. Right? Partition of this set. You remember partition of this set. So therefore, these two will be treated as different partition. That means the balls here, balls we are considering, n number of balls, x1, x2, xn. So they are distinct balls. They are not identical balls. So the balls are distinct here. This x1, x2, xn. These balls are distinct. So whether x1, x2, this is a block, or x2, x3 is a block, they are different cases, right? So therefore, here this SNK, we are actually distributing n number of distinct balls. And why this, why the blocks are, the boxes are identical. So here this partition that we get actually, that partition is here. This box is getting that partition into this is 2 plus the remaining n minus 2 and 2 plus n minus 3. I mean this box, whether a box will contain 2 elements, another box will contain n minus 2 elements actually, and the number of elements that box contains, okay, that will contain either 2 or n minus 2 actually. Okay, so that actually we are considering as, that we are considering as those boxes we are, not distinguishing that box number 1 will contain 2 elements, box number 2 will contain n minus 2 elements. We are not distinguishing as box number 1 and box number 2, right? Box number 1 will contain 2 elements, box number 2 will contain n minus 2 elements. So we are not distinguishing that which box will contain how many elements. Okay, so this box we are not distributing. Distinguishing. We are not distinguishing the boxes. So now again, my question is that whether you agree with my this definition of Stirling number. This is another way of defining Stirling number of second kind. Stirling number of second kind is another way of expressing, another way of defining. This is the number of ways to distribute n distinct balls into k identical boxes. Whether you agree, students, whether you understand, or if you have any doubt, you tell me.
The NPK?
Huh?
NPK.
Which one? NPK? Hmm? Which one will be your NPK?
The second one, that walls are distinct, boxes are distinct.
Oh, here you are saying. Yeah. This answer
Yes.
you are saying. Okay. So see this. Here we are taking boxes are also distinct. Huh? And what is this SNK? SNK, Stirling number of second kind. That is number of distribution of n distinct balls into k identical boxes. Okay. So if look at any such, distribution you will consider, the boxes are on order or on they are identical. So if we make the boxes also ordering, then each of this distribution will be multiplied by k factorial, that permitting. Yes, so the answer will be k factorial SNK. Do you agree with this?
Yes.
Huh? Okay, if we make the boxes, SNK means the boxes are on order or they are identical. If we make the boxes order, k boxes are there. So therefore, each one of this distribution that will be ordered in k factorial ways. So therefore, the answer will be k factorial SNK. Okay, you agree here? Okay, fine. So this third one, I will go to next distinct balls and here identical. You will able to answer this. And here no, some box may remain. Okay, yes, first we are considering yes, then no. Okay, some boxes may remain empty. Some boxes may remain empty. Okay, some boxes remain empty. So what will be this one? So whether you will get this SN1 plus SN2, the Stirling number of second kind plus SNK. So there are k boxes. Well, and this SN1 means distribution of n distinct balls into one box only. Okay, into one box. So therefore, other boxes will remain empty. One box remains empty. and here 2 boxes may remain empty. Okay, and here here this k minus 2 boxes will remain empty, k minus 2 boxes. Okay, and here no box remains empty, SNK. So whether you get this number, you check whether you agree, whether it is
Yes,
correct or not. At least, yeah. And that next case will be distinct, and here identical, and here no, right? So what will be this number? You tell me. This is able to answer after so many
S
discussions.
and K.
SNK, yes, SNK. This is just the definition of your that SNK. Okay. So the next case, total will have 8 possibilities. Here 4. Okay, where is this cursor? Okay, then 5th one. Here identical. All distinct is over for these balls. 2 identical balls now. And then distinct boxes. And yes, some boxes may be empty.
N plus k minus
Okay.
1 C.
Yeah, so I have already told you this is distribution of n identical balls into k distinct boxes, and some boxes may be empty. So this is exactly the solution of that non-negative integral solution of this equation, right? This is exactly that non-negative integral solution of that equation x1 plus x2 plus xk is equal to n, right? This is exactly that some boxes may be empty. So therefore we get this is n plus k minus 1, choose k minus 1 will be your answer. We have already discussed this. Fine. So 6th one is here identical, distinct, and here no box will remain empty. So what is this answer here you'll get?
N minus 1 C k.
With positive integral solution, right? Exactly this positive integral solution. Yes, positive integral solution of this summation xi is equal to n, I from 1 to k, right? Okay, so what was that number? N minus 1? Choose k minus 1. Yes, you are right. Okay, so then 7th possibility is your identical, and here we'll have this also identical, and here we will allow the boxes be empty, that can be empty. So what will be this number of ways? This number of ways that identical balls here distributing to identical boxes, and some of the boxes may be empty. So just you recall the definition of pkn, whether you get this number pkn that we have defined. What was this? Partition of this number n into at the most k parts. Partition of n into at the most k parts, right? This is what exactly you'll get. Will you think about this? Will you get this?
Yes.
Huh? Okay, you will get this. You think about this. And the last one is identical, identical, and this is no box will remain empty. How can we express this number of ways and what it will be? Tell me,
PKN
tell me.
minus K.
Yes,
PK.
pkn minus pk minus
No,
1. Huh?
no, minus K inside the bracket.
What are you saying?
Nothing. Yeah, right.
Okay, pkn minus pk minus 1n. Okay, no box will remain empty. Means this is exactly parts actually. Partition of n into exactly k parts. Because we are removing those partition into fewer than k parts. Partition of n into fewer than k parts that we are subtracting. So this is exactly the partition of n into k parts. Into k parts.
Ma'am,
Huh.
then can't we write it like PK of n minus K, like n minus K inside the bracket?
Tell me once again.
Like the expression that you have written for the 8th point.
Which one?
The 8th point.
Huh?
This PK minus 1.
Yeah. This was the last one. Okay.
So we can also write it as PK n minus K.
PK.
N minus
PK. Huh?
N minus K. In the bracket n minus K.
N minus K. Okay. PK n minus K. Achha. Whether we can write like this or not.
Like we first put one ball.
Oh, yes. From, yeah, exactly, we can write. Yes, you are right. From that recurrence relation also we are getting this number.
Yes.
Right? Yes, you are right. Exactly. Okay. It comes from that recurrence relation also. Yes. From recurrence relation, you can write. Yeah, you will get this. Both are equal. Yeah, correct. So this is about, okay, Stirling number of second kind I have told you, and Stirling number of first kind is left actually finally. Okay, just quickly I'll tell you what is Stirling number of first kind. We are saying second kind. Second kind means it won't be complete unless we tell about the first kind. Means first kind is still, that is, unfold, I can say. So, what is Stirling number of first kind then? Here, finally, I'll tell you this Stirling number of first kind. Number of first kind, and then the relation between these two. Stirling number of first kind we denote by small s. Small s nk. Nk are again positive integers with k less than or equal to n. Positive integers there. Positive integers with k less than or equal to n. So Stirling number of first kind. Well, before I go to this Stirling number of first kind, just actually it is related with that permutation of a set kind of thing, permutation of a set. So let me tell you about little bit about cycles in a permutation. Okay, I'll explain this through an example. Let us consider that let P1 is this. I'll write down the numbers 5, 2, 6, 1, 4, 3, 7, and P2 be another. I'm looking at the permutation. So of this I'll write down 6, 5, 1, 3, 7, 4, 2. Let P1 and P2 be permutations of this set one permutations of 1, 2, 3 up to 7 permutations of this. You understand by this? This means what? This meaning is that in this, I mean P1 of here P1 of this one in this actually in this permutation P1 will match 1 to 5. Huh? Okay, one image of 1 is 5. Image of 2 is this second place. The 2, I mean P of 1 is 5, P of 2 is 2, and that 3 will go to 6. Image of 3 is this third element here. Image of 4 is 1. Image of 5 is 4. Image of 6 is 3. Image of 7 is 7. This is what the permutation, I mean P1 max 1, 2, 3, 4, 5, 6, 7 to this one. This is what the notation we shall use for this permutation P1. And P2 max that one image of 1 will be that 6, image of 2 will be 5, image of 3 will be 1, image of 4 will be 3, image of 5 is 7, and image of 6 is 4, image of 7 is 2. Hope I have written correctly. These are the image. Okay, this is what we mean the permutation P1 and P2, the notation we use for this P1 and P2. Okay, if we put these numbers in this bracket, first bracket means here in the first place the number we get is that is image of 1. In the second place the number we have that is image of 2, 3, like this, it goes like this. Well, so this P1 in a diagram, through diagram, I'll draw this diagram for this P1. Okay, so P1, what it is doing is this, you see for this P1, this it is forming a cycle like this. P1 goes to 5, 5 goes to 4, and 4 goes to 1. Okay, so this image of, image of 1, I am writing in this way, is its image is 5. Then image of 5 is 4, and image of 4 is 1. So it is forming a cycle. This is a cycle. In this permutation P1, this is a cycle. And similarly, you are having this another cycle you see here in this permutation P1, that 3 maps to 6 and 6 also maps to 3, the reverse one. So this is also a cycle. Okay, cycle of length 2. Cycle of length 2 we can say. Okay, and then what about the others? That 2 maps to itself. That 2 maps to itself. Cycle of length 1. And 7, that also maps to itself. Okay, so this is what the structure of P1, cycle structure of P1. Cycle structure of P1. So here this P1 contains a 3 cycle. The cycle structure will be here, cycle structure of P1 is actually, it contains a 3 cycle and another 2 cycle and 2 1 cycles are there, right? 2 1 cycles are there. This is what the cycle structure of P1. Similarly, this P2, that P2 we can draw its diagram for this P2 is that you see the cycle here, that 1 to that is 6 to 4, 6 to 4, and then 4 goes to 3, 3 goes to 1. So this forms a cycle here in this P2. I'll write down here 1 that goes to 1 goes to 6 and 6 maps to here 4 and 4 maps to 3 and 3 maps to 1. So I'm sorry, this is 3 I'll write here. Okay. So this is 6 actually. 1 maps to 6, 6 maps to 4, 4 maps to 3. So this forms a 3 maps to 1, this forms a cycle. And the other one you see that 2 maps to 5 and that 5 maps to 7 and 7 maps to 2 here. So this cycle structure, I mean of P2 actually it contains a 4 cycle and this is the cycle structure and this another 3 cycles. So you could have written, I mean if we, this is the cycle structure, this is cycle structure only. But if I want to write in this form, what is this cycle I want to know? What is this cycle? Then I could have written 1, 6, 4, 3. This forms a cycle. And the other one, that 2, 5, 7, that forms a cycle. Okay, this is the permutation P2. See, this same cycle you can write in any order. Okay, any order, it doesn't matter. That, but in the cyclic order. 4, 6, 4, 3, 1 I could have written. Okay, I can change, it has to be in cyclic order, or I could have written this 7, 2, 5, I could have written. Okay, but if I write the other way, that 7, 5, 2, that will be reverse, right? 7, 5, 2, if I would have written 7, 5, 2. So this would have been reverse one. Okay, that 7, 5, 2, that would have been the reverse one, reverse cycle. So this is not the same one. Okay, this is not the same one. I mean, if you maintain this cyclic order, that 7, 2, 5, 5, 7, 2, so both all are same actually. We'll treat them as same. Okay, this is what the cyclic structure of these permutations P1 and P2. Well, now you understand by this cycle structure, a cycle composition of a permutation. Okay, so here in this P1, therefore P1 is having 4 cycles here. We can say that P1 is having here 4 cycles. 4 cycles, and P2 is having 2 cycles. P2 is having 2 cycles. and number of cycles in P2. Okay. So now we can give the definition of Stirling number of first kind. So this Stirling number of first kind S n k, small s n k is the number of permutations of 1, 2 to n, this set n. Okay, number of permutations of 1, 2 to n which have exactly k cycles, which have exactly k number of cycles, k cycles, exactly k cycles. So all, I mean that many number of permutations of this set which have exactly, these permutations have exactly k cycles. Okay, we'll see one example. Look at this example. Okay, let me scroll down, go to next page. Look at this example. So here, what will be the value of S small s 3 1 6? So what is this one? S3n. This is number of permutation here, number of, according to this definition, permutations of 1, 2, 3, 1, 2, 3, which have one cycle. Okay, which have only one cycle. Tell me how many? What will be this number then? So in this permutation of 1, 2, 3, that has only one cycle. That has only one cycle. So how many such permutation we will get? Tell. That is only one cycle. How many such permutations will get?
3.
Huh?
3.
3. You are saying 3.
One such person.
1. Only 1 or 3 or any other answer? Any other answer? Say here you can map, say let us map. 1 goes to 2, 2 goes to 3 and 3 goes to 1. This is one cycle you are getting. This is one cycle you are getting. Let me draw its diagram. 1, 2, 3. So I am saying that 1 goes to 2, 2 goes to 3, 3 goes to 1. This is one cycle I am getting. Any other cycle you can get?
Yes, ma'am.
3,
One.
Ma'am,
1
1, 2,
goes
3.
to
1
2
goes
goes to
to
1.
1 goes to
1 goes to 3, 3 goes to 2,
yes,
and 2 goes to
yes.
1. Yes.
Okay. 3 goes to 2, 2 goes to 1. I am writing straight this way. So this is the reverse one, right? This is the reverse one. That this cycle I'll write here. 1, I mean say, okay, 1, 2, 3 I'll write. So it is going mapping like this. 1 maps to 3, 3 maps to 2, 2 maps to 1. So you see this orientation is different. The reverse orientation, right? This one is clockwise, the other one is anti-clockwise. So therefore we will get that this clockwise, anti-clockwise, they will be calculated as a different one, different cycle. Okay, so this direction will be, orientation will be counted. Okay, orientation will be counted. So therefore the value of S31 is equal to 2. Is it fine? Okay. Do you agree with this?
Yes, ma'am.
Okay, good. So the next I will consider S32. Value of S32 will be what? What will be the value? S32. So this is permutation of 1, 2, 3 and that has 2 cycles. All permutations, this is actually all permutations of 1, 2, 3 with 2 cycles. With 2 cycles, that should have 2 cycles. So 3 numbers, how can you divide into 2 cycles?
Ma'am, the answer is 3. Like
Yes,
each element
answer,
can have
yeah,
single cycle.
yeah, one singleton. Definitely you will have one singleton. Yes, it will, you will have like this. Say 1 will map to 2, 2 will map to 1. This is a 2 cycle and another singleton, single cycle, that 3. Okay, this is one. Like this actually, the other one you can take 1, 3 and 1, 3 like this, and here you will take 2 a singleton. Okay, and the other one is that 2, 3, 2, 3, 3, 2 and that 1 will be singleton, right? You are correct. So therefore this S32 is equal to 3. Very good. Okay, so this is about the Stirling number of first kind. So this Stirling number of first kind is also, defined in another way. And just quickly, I'll tell you the relation between the Stirling number of first kind and second kind. So where is that relation? How they are related. And Stirling number of first kind is also defined in a different manner. Another definition is also there. So I'll come to that, and then I'll link with a Stirling number of second kind, this Stirling number of first kind. So for that, actually, we'll have a notation here. We'll have a notation that this is called notation for this polynomial. X square bracket and k. This notation I shall use for this polynomial x into x minus 1. It goes up to x minus k minus 1, x minus k minus 1. It goes up to this. This is a polynomial of degree k. Okay, so this notation, this is called, this is a name, this is called falling factorial polynomial. People use this terminology, falling factorial polynomial. Falling factorial polynomial. This is called falling factorial polynomial. It is a polynomial of degree k. So it is a polynomial of degree k. Polynomial of degree k. Well, so you understand this, and this, another definition of Stirling number is this. Another definition of Stirling number of first kind. Okay, another definition of Stirling number of first kind is SNK is the modulus of the coefficient of x to the power k in this polynomial, this falling factorial polynomial, right? So this falling factorial polynomial, you just write this as a polynomial, expand this, write that polynomial for, okay, that a0 plus a1x plus a2x square, that coefficient. So coefficient of xk in this falling factorial. This is what this Stirling number of first kind. So for example, let us see this.
Ma'am,
Falling
but where did you use n? Because s of nk is given, and in the definition there is no n.
okay. Acha. Okay. Xk
In the expression of xn.
in the expression of expression of x n. Well. Yeah. I'm sorry. This will be n. Okay. Yeah. Now it is, because n is bigger than k. No, n is greater than k. Yes, n is bigger than k. Yes, this was a mistake. Yes. This one. This is xn, of course. Okay. This was a mistake. Good. Very good that you have pointed out this mistake. Okay. So this is that falling factorial of Falling factorial of degree, that degree n actually we look, and that coefficient of xk. Okay, so here I am taking n equal to 3, let us take n equal to 3 I am taking here. So this I am getting, this is the 3, n equal to 3. So here n equal to 3 means what will be this polynomial, that x, okay, this k, I think I would have used some other number that would have been convenient, sm, okay, not to mix up with this s and k, okay, that would have been better also. Okay, shall I change if you won't mind? So this is in general actually, okay, or it will not matter also. If you like, you can, we can use a different parameter here, because k, n and k we do reserve for this Stirling number. So here when n equal to 3, s column factorial, this will be x into x minus 1, and up to how far I can go, in up to this, this is m, value of m you can say minus 1 actually. So up to this x minus 2 will go, right? This is what your this falling factorial, that box x, that 3. And if you expand this, write as polynomial, what do you get? S cube minus 3x square plus 2x. You'll get like this. So now here that number we are saying n equal to 3 and k equal to, suppose I will take, oh sorry, k equal to 2 I will take, S32, k equal to 2. So according to this, this second definition, okay, this second definition of S and k, it has to be absolute value of coefficient of x square. So that is equal to 3. And it is agreeing with our, the earlier definition we had given now, S32, that we are getting 3, right? Well, so this is another definition of this Stirling number of first kind. And now finally just I will write down this relation between the first kind and second kind. Okay, so that relation, I mean here this first kind we obtained in terms of this, I mean there's a falling factorial, actually the coefficient of x to the power k in this falling factorial of x, that xn actually, and this is another result, just I will write down, I am not proving. So this proof will involve a lot of, I mean that this logic here, a lot of things, and we don't have that much time to give all those proofs and all. So therefore, here, I mean, whenever you write this x n, I mean the falling factorial, here the coefficients here you have to write down. If I write the coefficients here as what I would have written here, this is a polynomial of degree n. So I will write this x a n, of course this is equal to 1, x n I would have written like this. Then this a n minus 1 x n minus 1, so polynomial of degree n, you could have written here a k x to the power k, like this it goes, that here we will have, it is decreasing a1, and that x factor will be there actually. So then if you write in this form, we are getting this Stirling number of first kind S and k is equal to absolute value of this ak in this expansion. Moreover, if you like to have that, in particular this subscript n to, I mean again you want to write this s n kind of thing throughout, okay, what I mean I was wanted to tell you that if you want to use this subscript one more actually, because we are looking at this expansion of this falling factorial xn. So if you like, you can write this second one also. Then it would have been this a k n n will be fixed here. So its absolute value or its modular, that is what your Stirling number of first kind. Okay, that is the reverse one. So the reverse thing, can we express this x to the power? I mean, here we have x to the power. I mean, I want to tell that this falling factorial, that box x, this n, we are writing in terms of powers of x. So the converse one, the power of x, can I write in terms of this falling factorial polynomial? In terms of falling factorial polynomial, that involves your Stirling number of second kind. So writing xn, we are writing this x to the power n in terms of falling factorial polynomials, falling factorial polynomials, falling factorial polynomials. Okay, that involves falling factorial polynomials involves this Stirling number of second kind, and that I will write the expression only. I am not proving. So it is like this. X to the power n is actually equal to this summation s n k, Stirling number of second kind, and falling factorial of x k, that k from 1 to n. This is what the relation between the Stirling number of first and second kind. Well, that's all for this combinatorics part. Your syllabus and in your exam, I mean the test I'll take next week, that on 10th, your portion is this much. Okay, till today what I have taught, that is your portion for your test on 10th. And let me tell you little bit about the type of questions you are going to get in the test on 10th of this month. So total, I mean, you will get 8 questions. 8 questions. All the questions will be fill in the blanks type. All the questions will be fill in the blanks, and in the blanks mostly you'll write only integers. Okay. In the blanks you have to write clear-cut integers. You should not write in terms of that, I mean, say 10 choose 5, 10 choose 5, this Stirling number SN, S53. So all these symbols and no symbols, nothing. Otherwise, that computer will not evaluate actually. The computer will not able to read all those notations, will not read and not be evaluated. So your answer will be integer answer. In the blanks, you will get only integer answer. Okay, only integer you will write. You will not leave in this any permutation, combination, Stirling, any no notation. Okay, in the blanks. And you will get 8 questions. All are filled in the blanks. But and one question will be of 5 marks. One question will be of 5 marks. Total 40 marks. Total marks will be 40 marks. And in one question, you may have 2, 3 or 4 number of blanks. Okay, that is 5 marks. No, I want to give you part marking. Those 5 marks, for that 5 marks, I will not keep only one blank, so that if your answer is wrong, then you lose full 5 marks. It is not like that. Those 5 marks I am dividing into 2 to 4 parts. 2 parts, or 2, 3 or 4. I will give all part marking. So that in one question, that is for 5 marks, and you may get number of blanks will vary from 2 to 4. At the most 4 blanks will be there and minimum 2 blanks will be there. Okay, so you have to fill up them. And total 8 questions I have told you. Okay, any other query? This is about the question type. I explained from my side. You can ask any question.
Navigation.
Ask.
Ma'am, navigation will be allowed or not?
No. Navigation will not be allowed. At a time you will get 2 questions. Navigation no, not allowed. 2 questions in a page. 2 questions at a time. 4 pages.
Like, what will be the count of questions and the time that we will have?
Time. A time I will give 1 hour time.
And number of questions?
8.
Okay. So like there will be 4 pages, right?
4 pages will be there.
Okay.
4 pages will be there. Okay. 15 minutes for 1 page. Okay.
And
or if you want a little more time, then I can ask also, because you are having 2 hours class. So shall I make 1 hour 10 minutes?
Like, what will be the type of the questions? Will it be fill in the blanks, or like we have to type a proof or something?
No. Okay, fill in the blanks. No, okay. That is fill in the blanks. See, even if it is a proof thing, you'll prove certain things. I'll ask in those steps some numerical value you'll get. Definitely you will get the numerical value. Okay, that question will be framed that in that step, what is your number you have got. Understand?
Answer will be
you have to fill up only the blanks. You don't have to write all the detail. You will not get any place for writing your proof. Okay. Got it? That proof will do on your rough work, and you'll only fill up that blanks with integer value, with a number. With integer value, you'll fill up the blanks. Got it?
Yes, ma'am. Got it. Yes, ma'am.
Okay. So shall I increase the time little bit? 1 hour 10 minutes shall I give?
Yes, ma'am. Yes, ma'am. Because there was
2 hours. 2 hours.
We are having class. Ma'am, there are many times delays in Moodle, like due to some glitches. So I think the extension would help.
Okay. So that time then, how much time I'll give you? Tell me.
Ma'am, 1 hour 15 minutes or anything. Ma'am, 1 hour 15 to 10, man, like.
Okay. 1 hour 15 minutes then I'll keep. Okay, fine.
Okay, thank you, ma'am.
1 hour 15 minutes I'll give you. Okay. Tell me.
Ma'am, would it be possible like decrease 10 minutes, but like allow us with navigation or something? Like maybe don't give us that much time, but allow navigation in the test.
Oh, navigation will not be allowed. Otherwise, lots of problem will happen. Navigation will not be allowed. I can give you extra time. Time can be given, but navigation will not be allowed. Okay. Navigation.
Okay, got it.
Yeah. Okay.
Is it something with the platform that navigation isn't allowed, or?
Yeah. Moodle platform. All of you, I am telling again. Moodle platform. You are having this, account, I think, in the Moodle. Otherwise, they will send from this Moodle, this Moodle people. Okay, I have already told them. In ERP, your name should be there actually. Okay, because they will collect your names from ERP only. Okay, if your names are not appearing in ERP, then they may not able to send you the link. They will send you the link, and I will also send you the link, the Moodle link only. Last time you have written test, no, you don't have any Moodle account. Some must be having Moodle account, all of you. Okay, it is fine. Acha, about these questions, that practice problems I had given. So please do solve the practice problems, and Wednesday class I'll discuss the problems. Wednesday and Thursday we are having 2 days in hand. Or any other day. I think actually I'll be out of station from tomorrow for few days. So if I go outside, then I may not able to. I may take a class through Google Meet, but Microsoft Team will not support outside. I think so. I may not able to Oh, I can share the board. It may not record. Fine. Okay, so Wednesday class, if I am out of Wednesday class, if I am out of station, I'll take through Google Meet and I'll share the link. Google Meet link, I'll send you through ERP. Your ERP, whatever contact I make you through your ERP mail only. You must check your ERP mail. Okay, so Wednesday will clear your doubts of that practice problem and any other doubts you have. Okay, I'll send you Google Meet link. I think Microsoft Team will not support if I am outside. Okay. Okay, that's all then. Have a nice day.
Thank you.
Okay.
Thank you, ma'am.
Thank you, ma'am.
Welcome.
Thank you, ma'am.
Welcome.
Thank you, ma'am.
Welcome.